be focused on designing the greener energy conversion for a sustainable future. So humankind always requires an energy, and it has become an indispensable part of our day-to-day life. In the past, the non-renewable energy resources such as oil, coal, natural gas and nuclear energy grabbed the opportunity to become a dominating force in the energy sector. However, the excess consumption and reliance leads to the serious environmental and also the water pollution, in addition to that global warming. According to the International Panel of Climate Change, you can see that there is an exponential increase in the temperature and an average temperature of 1.2 to 1.5 degree, and we all experienced in the last year, July, which is almost more than 50 degree record high temperature. However, there was a good news during the COVID time. So, almost a 6% reduction in the CO2 emission. By 2021, it impacted the 36.4 gigaton of CO2 emission, and according to the 2023, it's about 43.2 gigaton of CO2 into the environment. If you look at this bar diagram, India stands out to be in the third position, which emits a lot of CO2 into the environment. Considering the present population close to 8 billion and expected to increase about 9.5 by 2050, there is an increase of 30% demand of the energy requirement. In that case, hydrogen is one of the front runner because it has a 3 times high energy density, eco-friendly nature, and also water is the only byproduct. Because of that, it has been extensively utilized in various applications, 55% in ammonia production, 85% in petroleum production and methanol production, and the rest is for 10%. If you look at the demand of hydrogen by 2050, there is a great increase over there, but at the same time we have to look at the hydrogen production. Still 48% we are depending on the natural gases, 30% oil, 18% coal and 4% electrolysis. That means still 96% we are depending on the non-renewable energy sources. To produce 1 ton of hydrogen, we are releasing 9 to 12 tons of CO2 into the environment. In this regard, our group is extensively working on to address 3 sustainable development goals. One is the zero hunger. So that means we know that ammonia is one of the main constituents for the food production, and this food production, this ammonia is industrially established, produced by the industrially established evaporation process. It releases almost 400 million metric ton of CO2 into the environment. So therefore, our group is also working on to convert the nitrogen by greener approach that's called electrochemical reduction of nitrogen to ammonia. In addition to that, we also know that nitrate is a water pollutant, so that we are working on that to convert nitrate also into the ammonia. I don't go much in detail about it. And then another aspect is that we are also directly working on the conversion of CO2 into value-added product. A step forward, so we are also working with the zinc. That means we are integrating the zinc batteries into the CO2 system, so that simultaneously converting the CO2 into the value-added products such as ethanol, methanol and so on are present in our group, and simultaneously we are producing the electricity as well. So that means we are eliminating the external power source, and whatever the energy which is producing it, so that itself we are utilizing it for the conversion of CO2 into the value-added product. So this is one of the thesis from one of my students. And this is the demo which I am not going in detail because of the shortage of time. And recently we have demonstrated zinc CO2 batteries of almost 400 hours of the stability. And using this zinc CO2 batteries we connected in series, we could able to produce the hydrogen. So we implemented to the water electrolyzer. And this is one of the new things, so because we might have heard about the metal air batteries. So metal air batteries is one of the promising energy storage technology. However, in the case of metal air batteries, it demands 4 electron process. The same thing, if we replace it by 2 electron process, so almost we can decrease the 50% of the energy requirement. In this target, we started, and we know that hydrogen peroxide is produced by the entrepreneur process, and it has been extensively used for various industrial applications. But the major challenging in this case is that it uses expensive palladium catalyst and also multi-step requirement. More importantly, the transportation, because it has a decomposition. So therefore, only around 60 plants around the world we do have. So we were working extensively on the zinc air batteries. Then the idea comes because the hydrogen peroxide is one of the byproduct during the oxidation reduction reaction. If we develop or design the catalyst which is selective only with respect to the peroxide production and integrated similar to the zinc air battery, So then we can consider this as a zinc peroxide battery. So then we recently started the peroxide production, and later this hydrogen zinc peroxide battery is one of the first paper reported from our group, and we demonstrated almost more than 260 hours by connecting 32 LEDs, and now we are working on to increase the production. I don't go much in detail about it. And then I am coming to the energy storage batteries. We know that, so people are extensively working on the lithium-ion batteries, and it has been utilized for the various portable application and so on. But it has its limited application, because when you consider the capacity is very low, and also energy density is also very small. So if you want to improve that, so we can replace that, and also people are extensively working on the replacing the non-cobalt catalyst in the lithium-ion batteries. So therefore, if we replace that cathode by the sulfur-based, so we can increase the capacity as well as the energy density. So then this can be utilized for the larger application purpose. With this, we started with the iron sulfur, and our group is working extensively on the aqueous sulfur-based batteries. When we started, because I always intend to work on something new, because a lot of people are working, so therefore it takes almost a longer time. So to establish this one, so it took almost 3.5 years, because the challenging part is the stability of iron in aqueous system. And this is the second report, because only one report is available, which is after 150 hours they replace the iron anode. In this case, we utilized the DMS as additive, and we did all the studies, and we could able to demonstrate up to 600 hours. And also almost if you go up to 1000 cycles, the capacity retention is reduced to the 60%. And move on to this one, again we are working on the zinc sulfur batteries. We know that zinc air batteries is also one of the promising. In the similar way, zinc sulfur, if you go with that, the capacity we can go more than 1200 milliampere hour per gram. Here also we utilize the additive in order to stabilize the zinc, because again the stable of the zinc anode is also quite challenging. But the interesting part in this case is that this is a polysulfide free batteries, because if you go with the lithium sulfur batteries or sodium iron sulfur or sodium sulfur batteries, the polysulfide shuttling, so that the capacity and also the stability is quite challenging. However, in this case we do have the stability. We have utilized the additive, and also we demonstrated here for almost in this case also almost 700 hours of the stability, and now we have applied for the patent as well. And now we are working on to a larger pouch cell, so that we targeted for a little bigger application. So now coming to the actual picture. So because sodium ion sulfur, we started actually in our group sodium ion sulfur batteries. So when we started this, so we have a lot of problem with the polysulfide when we design. So therefore we have to design a catalyst which can handle the polysulfide. So therefore the amount of sulfur will not go into the solution, and we can hold it for the longer stability. With that concept, we introduce the ionic liquid, and during the mechanism, the discharging process, we do expect HS minus. This HS minus is not stable at all. So therefore immediately it formed in the H2S. So during this time, so the idea comes that how to address this issue apart from the battery application also. Then we realize that we know that H2S is also one of the pollutant. So I am not going to discuss about the battery, I will come directly to this one. H2S is one of the pollutant. Industry is also producing and also naturally present. If you are exposed to 5 ppm, it is not good for the health, and if it is more than 1000 ppm, it is lethal. And industrially, so they are doing this cloud process in order to do the desulfurization. The major challenging of this one is that to produce 1 metric ton of sulfur, they are utilizing 4.4 metric ton of hydrogen, which is wasting as a steam. And hydrogen is also produced by electrolysis, by electrochemical water splitting. However, the energy requirement is 1.23. So if you use this H2S as a hydrogen source, this can be one of the promising technology. However, if you go with the electrochemical approach, it's a nightmare when you have a sulfur in the solution. So alternatively, we have a thermolysis, photocatalysis and plasma technology, and each technology has both pros and cons. And if you look at the overall limitations, it demands a high temperature. When it demands a high temperature, especially when you have a sulfur, then maintenance of the catalyst, because it undergoes poison and surface and so on. So therefore, in our group, what we are doing is that this is our typical electrochemical water splitting, right? We expect the hydrogen production at a zero potential with respect to the standard hydrogen electrode, and 1.23 at oxygen evolution reaction. So just give me a few minutes. So if we replace, because we are aiming at hydrogen production, if we replace this oxygen evolution reaction, because in the oxygen evolution reaction we do not expect any product at all. The same thing if we replace by the sulfide oxidation reaction, using H2S as a source, we can reduce the energy almost 6 to 7 times. So the potential requirement to do this is only 0.14. As I said that when you have a sulfur, the chemistry is not so simple. So therefore we are playing here that high solubility versus low solubility. We are controlling the potential so that we do have the polysulfide which can dissolve in the solution, and we are not allowing to deposit on the electrode surface, so the stability of the system can be increased. But again we have a lot of challenges with this, and we demonstrated here. So we applied for the patent, and here you can see that when you have the H2S in the solution, there is increase in the current here. This is due to the sulfide oxidation reaction. To prove that this is due to the sulfide oxidation reaction, we have done some of the control experiment. You can see that in the object, this is nothing but electrochemical water splitting. The potential requirement in this case, and compared to the H2S sulfide oxidation reaction, we can save almost 1.25 with respect to our own catalyst, and according to the thermodynamic potential, we can save almost 1 volt of energy. That means it's a great ball. So this again we motivated by that we replace 1.2 volt battery. I'm not sure whether the bubbles are, you can see that the lot of bubbles on the electrode surface, and yellow color in the solution. Yellow color in the solution is clearly says that this is the polysulfide in the solution, not deposited on the electrode surface. In the absence of H2S, we cannot see any such kind of a thing. That means 1.2 volt is not enough to drive the reaction to produce the hydrogen. Moving forward, again we have done lot of stability tests, because this is one of the challenging part when you have H2S in the solution. At the same time, we try to monitor the changes in the solution also. We can see with the main challenge in this case of electrophotolysis is that every 30 hours we need to replace the solution, because the turbidity in the solution is increases due to the excess amount of polysulfide formation. So that at present we have been working on the in situ generation of the thiosulfate. Can you just press this movie? And this is a movie which is demonstrating that it's not about 1.2 volt, or it's not about 0.8 also. We need only a 0.3 volt in the presence of H2S to produce the same amount of hydrogen compared to the electrochemical water splitting. And just another one. And you can see that using the same catalyst, this 0.3 volt is not enough to do the hydrogen production, because we did not see any such bubbles. And many industries came forward to upscale this one, and we demonstrated with the prototyping especially. And that time we calculated the total amount also at the laboratory level, and energy efficiency. The energy which is required for the electrochemical water splitting is 37 kilowatt hour per meter cube. In the case of H2S electrolysis, we need less than this one. Time is over. Okay, with this I'll just stop it here. We have also been working on the nano generator. Just I wanted to give some examples on the conversion of the waste to the energy through the mechanical motion. If I just have it quickly, I can go through it. And apart from that, we have also extracted the sulfur. This sulfur we are utilizing for the sulfur-based batteries. And as sir was also discussing about the circular economy, and we are also utilizing the waste plastic, and also that a copper wire, especially with this electric wire. So using this, we are developing the nano generator, especially a chain nano generator, and through the mechanical motion, so we are creating the energy. Can you just tap on this one?
I think
I'll stop. And this is how we are demonstrated, and yes, some companies have come forward. We're just moving on to the next one. And for a practical application, so this is on the, can you just press it? On the treadmill. So because especially nano generator is for the using as a self-power for the sensor application, so for that we demonstrated here. With this I'll just stop it here, and I am happy to take up any questions because of the time, so that I can address this later as well.